Hi. My name is Wisdom, and
I'm Jashin.
yeah, so we'll be discussing about our final project for this course, and we worked on the application of machine learning in predicting the long-term behavior of materials in civil engineering. So a little background information about our project. We decided to work on three, because we have like different behavior that affects concrete on a long-term scale. But we choose to work on creep. So creep is like the time-dependent deformation of a structure, and this occur over a long period of time when you have a constant apply load on the structure and you have an increasing strength. So like the graph you have on your far right, you can see the total strain of the structure is increasing, and that is a log scale of over 1,000 days. So most times we don't have like the capacity to do this experimentally. So we want to come up with like a computational model, or rather say a machine learning model that can capture the behavior of this structure from experimental data that we have already. What people have been doing in the past, they're like empirical models that they just fit the curve to this model, to this experimental data, and they use that, but this doesn't give a very accurate prediction of this creep affecting concrete. So our project goal is to develop machine learning model to predict creep behavior under different conditions. So and also compare different kinds of model and look for like the most effective models to use. Our data was gotten from Northwestern Library, specifically KIM 2010 CRIP data, and some of the features we have from this data are like the material properties, quarter to semen ratio, also like the time variable. So the time variable was in hours for all of the parameter, and the order of creep strength was in the 10 of 10 power minus 6 per megapascal. We use four model, the random forest model, the gradient boosting model, the XG model, and the neural network. We decided to use these four different models because of their unique features in terms of capturing complexity in whatever data you said you're using. So this is like the four network that the four models that we decided to use for this project. Yeah, and the evaluation metric we used for these models was the mean square error, the MNS. Of course, we know we use this to measure like the average difference between the predicted data and the actual data. And of course, we also like the coefficient of correlation to see which of them it's closer to one. Of course, that is like the most effective model. So these are the tables that we got when we compared the four different models.
So talking about the feature importance, we're testing the random forest feature and exposed features on modules, and we can see that the part chart shows the contribution of each features to the random forest model prediction. On the left side, you could see the FC28 and Edge domains the calculations, which means it contributes a lot in this module, and the same as the XGBoost module. And then we plot the feature correlation. It displays the correlation coefficient between all features. We see the strong correlation between FC28, which was 28 days compression strength, and the cement content. And also we see the negative correlation between the water to cement ratio and the 28-day compression strength, suggesting that the higher water content reduces the strength. And this plot compares the training and the validation loss over 100 training steps for natural network. So we can observe that the training loss steady decrease, showing that the module is learning effectively. Talking about the conclusion of our project, um, we test four models, and the best model is XG boosting because it have the highest R square value and have lowest MSE. And then for the natural network, it's slightly underperforming, probably because the potentials for further optimization. And the property influence, we see that the material properties such as FC28 and water cement ratio significant influence the creep behavior. And also, the time is the most important variables to the creep behavior since it's time-dependent behavior. And for the future works, we are trying to get more creep data, for example, to add more temperature and humidity they are using. Thank you.
Thank you.